All right, so this is my second attempt at a video reassessment problem, just aiming trying to get a higher grade and just also preparing for the final in the process. So I just chose a problem from the book. It's an example problem, but it's a tough example problem because you really have to think about it. So the problem reads: Saturn is 1.43 times 10 to the 12 meters away from the sun. A rocket travels along a line from the sun to Saturn at constant speed of 0.9 c relative to the solar system. How long does the journey take measured by an experimenter on Earth? What about as measured from experimenter on the rocket? All right, so basically okay, let's think about it. Okay, so basically the rest frame for the rocket is what I'm going to call frame S prime. That's like an astronaut on the rocket. So that's the rest frame for the rocket. And therefore, an experimenter on S actually sees the rocket going from the sun to the Saturn. So it's traveling a distance delta X, while as in the rest frame S prime, delta X is equal to 0, because as far as the astronaut on the rocket, all he sees is the sun flying past him and Saturn flying past them at a velocity of negative 0.9 c. So that's why I say here delta x prime is 0 in that frame, and therefore in the problem it gives us basically delta x as seen from the Earth. The distance from the sun to Saturn is 1.43 times 10 to the 12 meters. All right, so as far as the experimenter on Earth, he sees it just as a basic problem. He basically he knows the distance and he knows the speed that the rocket is traveling at. So right here, basically the challenging part where you can't use your intuition doesn't yet apply. So basically just the time, you get what I'm saying, the time that he sees that it takes the rocket to go from the sun to Saturn is basically just the change in x divided by the velocity. So basically for that I get basically he sees it takes 5,300 seconds basically. Now for the astronaut, things get a little tricky. For the astronaut on the rocket, things get a little tricky because all he sees is things flying past him. So his delta x is equal to 0. So therefore his time, which is the proper time, t prime, is different. He's not going to have the same time as the astronaut observing from Earth. So therefore we have to use our time dilation equation, which tells us that basically the proper time is delta t times the square root of 1 minus beta. Well, we know beta is v over c times beta squared, where we know beta is v over c. So therefore, to calculate that, we just found out the basically the time as seen in the reference frame of the astronaut, or as the experiment on Earth. So as we see here, we just plug into our proper time equation. Into our time dilation equation to get the proper time, and therefore we see the proper time is 2,310 seconds, which is much shorter than the time as seen from the astronaut on Earth, which is very interesting. You know what I'm saying? We had two different times for the same event, but as we showed in class and throughout the book, that you get what I'm saying, these two different events won't have the same time. So yeah, that's pretty much it.